Welcome to Signed URLs. Welcome to the channel. Please consider subscribing. I produce videos daily, covering a wide variety of cloud topics with a focus on networking. Today, I'm going to walk you through implementing Google Cloud Signed URLs for EduTech University's digital learning platform. As you know, we've been facing challenges with securely distributing course materials, lecture recordings, and assignment files to our students. Signed URLs are going to be our solution. Think of a signed URL as a temporary, secure pass to access a specific file, like giving someone a visitor badge that expires after a certain time. This ensures only authorized students can access materials during their enrollment period. To understand the challenge we face, let me paint a picture of our current situation at EduTech University. We have thousands of digital assets, such as video lectures that can be several gigabytes, PDF textbooks, assignment files, and research papers. Right now, we are either making everything public, which violates copyright agreements, or managing complex ACLs for each student. Neither approach scales well. With signed URLs, we can generate time-limited access links on demand. When a student logs into our portal, we can create URLs that expire in 24 hours, ensuring they can download their materials but can't share permanent links. This diagram shows our current architecture and where signed URLs fit in. Setting up the service account. Before we can create signed URLs, we need a service account with the proper permissions. Think of this as creating a special user account that our application will use to sign URLs. Let me explain each command in detail. The first command, gcloud IAM service accounts creates a new service account. The name, EduTech URL Signer, is what we'll use to reference it in other commands. The display name flag sets a human-friendly name that you'll see in the Google Cloud Console, and the description helps your team understand what this account is for. The second command generates a key file. This is a crucial step. The gcloud IAM service accounts keys command creates a JSON file containing private keys. We're saving it to ~edutechsignerkey.json. The tilde character represents your home directory. The IAM account parameter needs the full email address of the service account, which always follows the pattern. Account name at projectid.iam.gserviceaccount.com. The JSON file contains several important fields. The private key is the cryptographic key used to sign URLs. The client email identifies which service account is signing, and the project ID shows which GCP project this belongs to. Guard this file carefully. It's like a password that never expires. The last command, gcloud IAM service accounts list pipe grep EduTech URL Signer, verifies our account was created. The pipe symbol sends the output to grep, which then filters for lines containing our account name. Now, we need to set up our storage buckets properly. At EduTech, we organize our content into three main buckets: course materials, lecture videos, and student submissions. Let me break down these permission commands. The first command, gcloud storage buckets add IAM policy binding, is granting permissions to our service account. The gs://edutech course materials is the bucket name. The GS stands for Google Storage. The member parameter specifies WHO gets the permission. Notice it starts with service account : followed by the email address. The role parameter is what permission we're granting. Here, it's set to roles/storage.objectViewer. Object Viewer means the account can read files but not modify or delete them. This follows the principle of least privilege. Only give the minimum permissions needed. We repeat this for each bucket. Notice how each bucket can have different permissions. For example, for student submissions, you might want to grant object admin so students can upload files. The last command is special. The command gcloud projects add IAM policy binding grants a project level permission. The service account token creator role is required for the signing process itself. Without this, even with bucket access, the service account can't create signed URLs. Think of it as giving the account permission to use its own signing capabilities. Creating your first signed URI. Here's the moment we have been waiting for. Creating our first signed URI. Let me explain every part of this command in detail. gsutil signer is the command that creates signed URIs. gsutil is Google's command line tool for working with cloud storage. The signer subcommand specifically handles URI signing. The D4H flag sets the duration, which is how long the URI remains valid. You can use different formats. 4H for 4 hours, 30 meters for 30 minutes, 7D for 7 days, or even 6M for 6 months. After this time expires, the URI stops working completely. Next comes ~edutech signer key.json. This is the path to your service account key file we created earlier. The tilde is a shortcut for your home directory. Finally, gs://edutech course materials /cs101/lecture01.mp4 is the full path to the file. It breaks down as gs:// the protocol, edutech course materials, the bucket name, cs101, the folder, and lecture01.mp4, the file name. When you run this command, you will see output showing the HTTP method, GET for downloads, expiration time, and the actual signed URI. The URI contains several parameters like xgoog algorithm, the signing method, xgoog credential, which service account signed it, xgoog date, when it was created, xgoog expires, the validity in seconds, and xgoog signature, the cryptographic signature that proves authenticity. Let's explore the powerful options available for different scenarios at our university. Each flag in these commands serves a specific purpose. In the first command, we're using D3 hours 30 minutes, which shows you can mix hours and minutes. This is perfect for timed exams where you need precise control. The second command introduces input, which changes the HTTP method. While GET is for downloading files, PUT is for uploading. This is how we allow students to submit assignments. The signed URL will only accept PUT requests. If someone tries to use it to download, it will fail. The third command adds C_application/PDF, which enforces the content type. This ensures students can only upload PDFs, not Word documents or executables. It's a security measure that prevents students from uploading potentially harmful files. The fourth command shows uhttps://cdn.edutech.edu, which sets a custom endpoint. This is powerful when using a CDN, or content delivery network. Instead of the standard storage.googleapi.com URL, it creates a URL using your custom domain. The signature still works because it's based on the canonical URL. You can combine these options too. For example, a command using input, D2H, and C_application/PDF creates an upload URL that expires in 2 hours and only accepts PDFs. Perfect for assignment submissions. Real-world university scenarios. Let me show you how we handle common scenarios at EduTech University with actual commands you can use. For course enrollment, we use -D180D, which means 180 days, or roughly a semester. The D stands for days. This gives students access to the full course bundle ZIP file for the entire semester. The assignment submission scenario is clever. Look at this command. We're setting a deadline variable with the exact date and time. Then we use the command date-d deadline plus %s. This converts the deadline to seconds since the Unix epoch. The s at the end tells gsutil we're specifying seconds. This ensures the upload URI expires at exactly 11:59 p.m. on March 25th. For guest lectures, -D48H gives visitors 2 days to watch the recording. This balances accessibility with protecting our content. The library reserve example uses -D24 hours, mimicking traditional library policies. Notice the -R flag. This would enable resumable uploads and downloads for large files, although it is not shown in the actual command. Students can check out digital materials just like physical books. Each command creates a URI tailored to the specific use case. The expiration times are not arbitrary, they match our academic policy. Implementing this programmatically. While gsutil is great for testing, in production, you'll want to generate signed URLs programmatically. Let me walk through this Python code line by line. First, we import the necessary libraries. From Google.Cloud, import storage gives us Google's Cloud Storage Library. Datetime and timeDelta help us work with time. JSON is for reading our key file. The AdoTech URL Signer class encapsulates our signing logic. In the init method, we open and read the JSON key file. The withOpen statement ensures the file is properly closed after reading. We store the credentials in self.credentialsinfo. Then we create a storage client using client.fromServiceAccountInfo. This is important. We're explicitly passing our credentials rather than relying on environment defaults. The generateSignedURL method does the actual signing. It takes the bucket name, for example EduTech course materials, the object name, which is the file path, and the expiration hours with a default of 4. Inside the method, we get the bucket object, then the blob, or file, object. We calculate the expiration by adding hours to the current UTC time. The generateSignedURL call uses v4, which is the latest signing version, passes our expiration time, sets the method to get for downloads, and uses the credentials from our JSON file. The second function, generateUploadURL, shows how to create upload URLs. The key differences are: the method is set to put for uploads, and we add content type is set to application/PDF to restrict uploads to PDF files only. When you run this code, it returns a complete signed URL that students can use immediately. Security best practices. Security is paramount when dealing with educational content. Let me explain each security measure we implement. The first command shows IP restriction using the -r flag followed by IP ranges. The RFC 1918 ranges are CIDR notation IP ranges, and these cover common private network addresses. This means the signed URL will only work from campus networks. If a student shares the URL with someone off campus, it won't work. The rate-limiting code uses Redis, a fast in-memory database, to track how many URLs each student generates. We get the count with redis.get, adding the student ID to make the key unique. If they exceed 100 URLs per hour, we raise an exception. This prevents students from mass generating URLs to share or sell. Why these specific measures? IP restrictions protect high-value content like exam solutions. Rate limiting prevents commercial redistribution. For example, we caught one student trying to sell access to course materials on a forum. The security checklist items are critical. Rotating keys annually prevents long-term exposure if a key is compromised. Monitoring for unusual patterns might catch a student sharing their account. Short expiration times limit the damage if a URL is shared. IP allowlists add an extra layer for sensitive content. Remember, each security measure adds friction for legitimate users, so only implement what's necessary for your content sensitivity level. Monitoring and troubleshooting are crucial, because even the best systems need watching. Let me explain some useful monitoring commands and how to solve common issues. The first command, gcloud logging read, queries cloud logging. Using a filter for resource type equals GCS bucket targets your storage logs, and another filter for JSON payload URL type equals signed specifically finds signed URL events. The limit parameter, set to 50, shows the last 50 entries, and the format parameter, set to JSON, makes the output machine readable. This helps us see who is generating URLs and how often. The second troubleshooting command checks IAM permissions. The command gcloud projects get IAM policy gets all permissions for your project. The flatten and filter flags help you find only the permissions for your service account. If signed URLs are not working, this is a great way to confirm the account has the right roles. The gsutil get command checks bucket level permissions. The pipe to grep filters for our service account. This verifies that the account can access the specific bucket. The test command creates a 1-minute URL for a test file. This is perfect for debugging. If this works but your production URLs do not, the problem is in your code, not the permissions. Now for some common issues and solutions. A 403 forbidden error usually means missing permissions, so check both project and bucket IAMA URL expired error, especially with seemingly valid URLs, often indicates clock skew, which means your server's time is off. An invalid signature error means you are using the wrong key file, or the file itself is corrupted. Slow generation happens when you hit API rate limits. To fix this, you can implement caching to reuse URLs. Here's a pro tip. Set up alerts for when your error rates exceed 1%. Catching issues early is key to preventing student frustration. Cost analysis and optimization. Let's talk money and look at these cost optimization commands in detail. The first command, gsutil lifecycle set lifecycle.json, applies lifecycle rules to automatically move old files to cheaper storage. The JSON file defines rules. After 30 days, files move from standard storage, at $0.02 per gigabyte per month, to nearline, at $0.01 per gigabyte per month. After 365 days, they move to archive, at $0.0012 per gigabyte per month. This can cut storage costs by 90% for old content. The second command enables CDN caching. The parameter cache mode equals cache all static tells the CDN to cache everything it can. This reduces egress costs because repeat downloads come from edge servers, not your bucket. CDN bandwidth is much cheaper than direct cloud storage egress. The third command shows video compression. The ffmpeg command re-encodes videos using H.264 for video and AAC for audio codecs. This can reduce file sizes by 50 to 70% without noticeable quality loss. Smaller files mean lower storage and egress costs. The BigQuery SQL query analyzes your costs by region. It reads from cloud storage access logs, sums up the bytes transferred by location, and calculates costs at $0.12 per gigabyte, which is typical egress pricing. This helps identify whether certain regions are driving up costs, which would indicate you might need a CDN presence there. Looking at our pie chart, egress dominates costs each month. That's why CDN caching and compression are so important. The $200 storage cost shows our lifecycle policies are working. The $5,000 CDN cost is worth it, as without it, egress costs would be even higher. Integration architecture. Here's how signed URLs fit into our broader architecture at EduTech University. This is the system serving our students across 5 campuses. Students interact with our React-based portal. When they click on a resource, the front-end calls our fast API backend. The backend authenticates the student, checks their enrollment, and then generates a signed URL. We cache generated URLs in Redis for 5 minutes to reduce load on the signing service. The URL is returned to the front end, which either displays it in an embedded player or provides a download link. This architecture handles concurrent users during peak times like assignment deadlines. The beauty is that the actual file serving is handled entirely by Google Cloud Storage. We just orchestrate access. Advanced signing scenarios. Let's dive into these advanced signing scenarios with detailed explanations of each command. The batch signing script uses a for loop in Bash. The script uses the gsutil-ls command to list all files in the gs://edutech course materials/cs101/week1/ directory. The loop iterates through each file, running gsutil-sign URL and appending the output to a file named batch_urls.txt. This is much more efficient than signing files one by one manually. The conditional signing based on GPA shows bash scripting. We check if the student GPA variable is greater than 3.5 using the -GT operator, which stands for greater than. The double brackets are for conditional tests in bash. Honor students get 90-day access while others get 30 days. This rewards academic achievement with extended access. The custom headers example uses -H flags. Each -H adds a header to the signed URL. X student ID and X course code are custom headers we invented. The X prefix indicates they are custom headers. When someone uses this URL, these headers are sent with the request. Our logging system captures them for analytics, so we can track which students access which content without putting sensitive data in the URL itself. The partial content example adds a range header. The range header, by specifying a byte range, can be used to request only the first megabyte of the file. This is perfect for video streaming, as players can request small chunks as needed rather than downloading entire multi-gigabyte files. It enables seeking in videos without downloading everything first. These advanced techniques solve real problems. Batch operations save time during course setup. Conditional access rewards students. Custom headers enable analytics, and byte ranges improve the video playback experience. Automation and CI/CD are key to managing signed URLs at scale. Let me explain how we do this with a GitHub Actions workflow and a Python script. The workflow file should be saved in the .github/workflows/deploy-content.yml file in your repository. It triggers on a push event when files in the content directory change. This means whenever a professor uploads new materials, the automation kicks in. In the workflow, the action/checkout at v2 action downloads your repository code. The setup gcloud action installs and configures the gcloud command line tool. The service account key comes from GitHub secrets. You should never put credentials directly in your workflow file. The upload step uses gsutil with the M and R flags. The M flag enables parallel uploads, which is much faster for many files. The R flag copies recursively, preserving the folder structure. The content/star syntax means everything in the content folder goes to the bucket. The preview URL generation loops through the uploaded files. The command, find content type F, lists all files, but not directories. For each file, we create a 7-day preview URL. We use specific syntax to remove the content/prefix from the path, which is a feature known as bash parameter expansion. The Python script then reads these URLs and sends an email. Using MIME multipart, we create an email with both text and potential attachments. We construct the email with subject, from, and to addresses. The email body includes all the preview URLs so instructors can review the content before students see it. The SMTP section connects to your email server. The start TLS function enables encryption. We use an environment variable for the password, because you should never hard-code credentials. This automation ensures quality control while saving hours of manual work. Let me walk you through the actual student experience. This is what makes all our technical work worthwhile. When Sarah, a computer science major, logs into the portal, she sees her enrolled courses. Clicking on CS101 triggers our backend to generate signed URLs for all available materials. She can stream lectures directly in the browser, download PDFs for offline reading, or submit assignments through upload URLs. The experience is seamless. She never sees the complexity behind the scenes. If she tries to access materials after dropping a course, she gets a friendly error message. If she shares a URL with a friend, it will not work after expiration. This protects our content while providing a smooth experience. If you are currently using a different system, here is how we migrated EduTech's 10 terabytes of content. Let me explain the migration script commands. The gsutil rsync command is powerful for migration. The M flag enables parallel transfers, which is crucial for 10 terabytes of data. The rsync subcommand synchronizes directories, only copying changed files. The R flag works recursively through subdirectories. The D flag is important. It deletes files in the destination that do not exist in the source, ensuring an exact mirror. The path/old storage/courses is your source directory, which could be a mounted network drive or local storage. The destination is your new cloud storage bucket at gs://edutech course materials. This command preserves your existing folder structure. The Python database update script uses scicopg2 to connect to PostgreSQL. The update query changes all records where the storage type is legacy to use GCS for Google Cloud Storage instead. We also set the bucket name. The connection.commit call is crucial. Without it, changes will not be saved. The validation command creates test URLs for migrated content. The wildcard character in the path tests multiple files at once. The 1-hour expiration is perfect for testing, as it is long enough to verify access but short enough to minimize security exposure. Run rsync multiple times. The first pass might take days for 10 terabytes, but subsequent runs only sync the changes. Test thoroughly with a pilot group before switching everyone over. Keep the old system running in read-only mode as a backup. Document every step, as you might need to migrate again someday. Optimizing performance is crucial when thousands of students access materials simultaneously. Let me explain each optimization command and technique. The first command, gcloud compute backend buckets update, configures cloud CDN. The enable CDN flag turns on caching at Google's edge locations worldwide. The signed URL cache max age equals 3600 parameter is critical. It tells the CDN it can cache signed URLs for up to 3600 seconds, which is 1 hour. This means if 100 students request the same file within an hour, 99 of them will get it from the nearby CDN cache instead of your bucket. The cron job runs at 3 a.m. daily, when usage is lowest. The script pre-generates URLs for popular content, for example, the top 100 most accessed files based on analytics. When students wake up, the URLs are already cached and ready. The Redis connection pooling code is important for high traffic. The connection pool command creates a pool of reusable connections. The parameter max connections equals 100 limits how many simultaneous Redis connections we maintain. Setting socket keep alive to true prevents connections from timing out during idle periods. Without pooling, each request would create a new connection, which is slow and resource intensive. The retry decorator is an elegant Python feature. The @retry command automatically retries failed operations. The wait exponential parameter means it waits progressively longer between retries. 4 seconds, then 8, then 16, up to a maximum of 10 seconds. The multiplier equals 1 parameter controls how fast the wait time grows. This handles temporary failures gracefully without hammering the API. These optimizations compound. CDN reduces load by 60%. Pre-generation eliminates morning spikes. Connection pooling cuts Redis latency by 70%, and retries handle the remaining transient failures. Together, they let us handle beginning of semester traffic that's 10 times the normal load. Compliance and legal. Educational institutions face unique compliance requirements. Let me explain how our code ensures compliance. The Generate Anonymous URL function is crucial for FERPA, the Family Educational Rights and Privacy Act, compliance. Instead of putting student IDs directly in URLs, we create an anonymous hash. The hash lib.sha256 creates a one-way hash. You can't reverse it to get the original student ID. We combine the student ID with a secret salt, which is a random string only we know, to prevent rainbow table attacks. We then take only the first 16 characters of the hash. This is enough to be unique, but short enough to be manageable. This anonymous ID goes in a custom header, not the URL itself. This way, even if a URL is shared, there's no personally identifiable information exposed. The audit logging function is essential for copyright compliance. We hash the student ID again for privacy, but we log the timestamp, the resource accessed, the IP address, and the URL expiry time. The ISO format function creates timestamps in a standard format for easy parsing. Why does this matter? Publishers often require us to prove only enrolled students accessed materials. With these logs, we can show which resources were accessed and when, that URLs expired after their set times, and access patterns that would indicate sharing, for example, simultaneous access from different continents. For accessibility, signed URLs work perfectly with screen readers because they're just regular URLs. We ensure our CDN doesn't interfere with assistive technology. We also provide multiple formats through the same system. For example, a lecture might have video, audio only, and transcript versions, each with its own signed URL. Remember, compliance isn't just about following rules. It's about protecting student privacy and respecting content creators' rights. Future enhancements. Looking ahead, here are the exciting enhancements we're planning. Let me explain the ML-based pre-generation code. The Predict Content Access function showcases how machine learning can optimize signed URLs. We load a trained model that has learned from historical access patterns. For example, it might notice that students typically watch Lecture 2 within 24 hours of watching Lecture 1, or that most students access assignment templates on Sunday evenings. The Extract Features function would pull relevant data. What time is it? What content has this student accessed recently? What's their major? The model returns predictions as tuples of content ID and probability. If the probability exceeds 0.8, an 80% chance the student will need this content soon, we pre-generate the URL. This predictive approach solves a real problem: the morning rush when thousands of students log in simultaneously. By pre-generating URLs for content they're likely to need, we spread the computational load across quiet nighttime hours. Blockchain integration would work differently. Instead of storing URLs on the blockchain, which is too expensive, we would store hashes of transcripts. When alumni need to prove their credentials, we generate a signed URL to their transcript and can verify its authenticity against the blockchain record. VR content delivery is challenging because 3D models and volumetric videos are huge, sometimes 100 gigabytes plus. Signed URLs with byte range support let VR headsets stream just the parts of the model currently in view, making it feasible to deliver immersive educational experiences. Edge computing would run lightweight URL generation at CDN locations, reducing round-trip time to under 10 milliseconds. Instead of going back to your central servers, URLs could be generated right where students are accessing them. Let's wrap up with the key lessons from implementing signed URLs at EduTech University. First, start simple. Get basic signed URLs working before adding complexity. Test thoroughly. Nothing damages trust like students unable to access materials during exams. Monitor everything. You cannot improve what you do not measure. Document your implementation extensively. Your future team members will thank you. Most importantly, always think about the end-user experience. Technical elegance means nothing if students struggle to access their education. Signed URLs have transformed how we deliver digital education. They are secure, scalable, and cost-effective. I hope this guide helps you implement them successfully at your institution. Thank you for your attendance. Please consider subscribing to the channel.